enalapril. Enalapril is an angiotensin-converting enzyme inhibitor used in the treatment of hypertension, diabetic nephropathy, and some types of chronic heart failure. It prevents the conversion of the peptide hormone angiotensin 1 to angiotensin 2 and prevents vasoconstriction, which causes an increase in blood pressure. Enalapril is the first member of the group known as dicarboxylate-containing ACE inhibitor. It's on WHO's list of essential medicine, a list of the most important medication needed in a basic health system. Enalapril has been proven to protect the function of the kidneys in hypertension, heart failure, and diabetes.
Enalapril is pregnancy category D. There is evidence that suggests enalapril will cause injury and death to a developing fetus. Pregnant women are not advised to take this medication. Enalapril is secreted in breast milk and not recommended for use while breastfeeding. The most common side effects of enalapril include increase in serum creatinine, dizziness, low blood pressure, and dry cough. The most serious side effect is angioedema that often affect the face and lips, which endangering the patient's airways. Angioedema can occur at any point during treatment with enalapril, but commonly occur after the first few doses. Sequib developed the first inhibitor, captopril, but it had adverse effects such as metallic taste.
This is the structure of this drug. It consists of two carboxylic acid groups. On this side, the carboxylate ion binds to charged nitrogen of amino acid in binding site, while at the other side, the carboxylate group make direct interaction with catalytic zinc ion. It also consists of carbonyl group that form straight hydrogen bonds in ACA binding site, while on this side, secondary amine contribute to the molecule's low lipophilicity and poor oral availability characteristic. Phenylethyl group here mimics the hydrophobic side chain of phenylamino in angiotensin 1, while methyl group here mimics the side chain of alanine and it reacts with hydrophobic SAS1 pocket. Pyrrolidine also part of this structure. Carboxylic acid, carbonyl, amine, and benzene.
In the body, 60% of absorbed dose of enalapril is hydrolyzed extensively to enalaprillate, primarily by liver esterases and excreted unchanged. Ionization of the adjacent carboxylate in enalaprillate greatly enhances the basicity of the secondary amine, such as the pKa of the amine in this compound is 7.83, whereas in enalapril it is only 5.2. Thus, in the small intestine, the amine in enalaprillate will be primarily ionized and form a zwitterion with the adjacent carboxylate, but the amine in enalapril will be primarily
Enalaprillate are inhibitors which have two ionized carboxylate groups. In enalaprillate, one of the carboxylate group is involved in zinc chelation. These two chelating carboxylate oxygens make direct coordination to zinc with penta-coordinated geometry that appears to mimic the nucleophilic water and the carboxyl oxygen of the substrate in the tetrahedral intermediates during enzymatic reaction, while the other one interact with arginine group or other amino acid. The phenylethane side chain forms hydrophobic interaction with S1 subsite of the enzyme, while the methyl feed to S1 pocket and increase the binding affinity of the drug. The carbonyl group also form hydrogen bonding with angiotensin converting enzyme binding site.
This is how the drug protein structure looks like. From 3D view, the drug structure can be viewed from overall 3D view and ligand and pocket view. The drug protein structure also can be viewed from map of ligand protein interaction. Using a software which is ChemSketch, the structure of enalaprillate before and after minimization can be designed. The minimization also can be seen using 3D structures which are stick and balls, and space field structure.
Hydrogen bond acceptor and hydrogen bond donor of enalaprillate. HBA is a hydrogen bond acceptor, which is the electronegative atom. It provides the electron-rich atom to receive the hydrogen bond. HBD is a hydrogen bond donor that provides a hydrogen for hydrogen bonding. Based on the structure of an enalapril, there are 6 hydrogen bond acceptor and 3 hydrogen bond donor. Based on the Henderson-Hesburgh equation, pH is equal to pKa plus log, ionized drug over unionized drug. From a drug bank, we know that the pKa of the strongest acid is 3.13, whereas for the strongest base is 7.84. By substituting the value of pH and pKa into the Henderson-Hesburgh equation, the percentage ionization of strongest acid is 99.99%, whereas for the strongest base is 72.91%. So, we can conclude that enalapril is soluble in both acid and base.
We can predict the solubility of enalapril by using Lemke's formula. Enalapril is a polyfunctional molecule. We know that the total number of carbons in it is 18 carbons. So, by calculating the carbon solubilizing potential of each functional group, we conclude that the drug is water insoluble. By looking at the physical-chemical parameters, enalapril fulfills Lipinski's rule of 5. It's supposed to be orally active. However, it has a low oral bioavailability because the ionization of adjacent carboxylate in enalapril greatly increases the basicity of secondary amine. Therefore, in the small intestine, the amine in enalapril will be primarily ionized to form zwitter ion with the adjacent carboxylate. The formation of zwitter ions lowers the oral activity of enalapril. This explains why enalapril has a low oral bioavailability.
Enalapril is a competing prodrug which hydrolyzes into enalapril by carboxyesterase enzyme. Enalapril was developed partly to overcome the limitation of captopril. The sulfhydryl moiety was replaced by carboxylate moiety. However, there are additional modifications that can be made, which required in its structure-based design to achieve a similar potency to captopril. Enalapril, however, had a problem on its own. The consequence of the structural modification may have unfavorable ionization characteristics to allow sufficient potency for oral administration.